This is a problem involving parallel resistances, and it says what resistance must be placed in parallel with a 155 ohm resistor to make the equivalent resistance 115 ohms. So first I'm going to draw a little bit here. Here I'm going to make myself a battery. I don't know where to start here. And then I may want to draw some wires in here. There we go. Actually all the way across here. There, and then I'm going to put a resistor here, and in parallel I'm going to put a resistor here. And sorry that didn't quite line up here. There we go. Looks a little nicer. Now I have to try to squiggly my resistors in here. There we go. And one of them has a resistance of 155 ohms, and the other one is an unknown. Let's call this one R1, and we call this one R2. But what is given in the problem is that R total, or equivalent, is 115 ohms. There. Okay, well, this is parallel circuits. I do this one as a problem here for parallel circuits because for series circuits it's kind of trivial. Just plug in, add three numbers for three resistors, so I might as well do parallel circuits because they're a little tougher. It's not just add the resistors, but add the reciprocals. So 1R total equals 1 over R1 plus 1 over R2. And in this case, this one here is the unknown. So I do the algebra for that one. Therefore 1 over R1 equals 1 over the R total minus, as I get this here to the other side, minus 1 over R2. And then it's just a matter of plugging in numbers, looking for my calculator on my desk. So what I do is 1 over 115 should be the total, minus 1 over 155, and I come up with 0.002244. And when you come up with such a tiny number, then that tells you that you have to do one more step, and that is invert it, because what I just calculated is the reciprocal, so you have to invert it because of this one here in order to get R1. So I take that 0.002244 and divide it into 1, and I come up with 446 ohms. And so I actually gave the answer away for this problem here. Let me show you with a circuit construction, and I'm actually not going to use the FET circuit because I noticed when I used their construction, their circuit construction kits, that doesn't allow me to get up to 155 ohms, only to 100 ohms. So I would have to kind of use numbers like 15.5. In order to avoid that, I Google another circuit applet, and that's really what I type in. And the one that I do like is this one here. And at this point there's a little bit of too much in here. I don't know how to erase everything. I'm going to put a resistor right here, and it asked me to put in a resistance, so I'm going to put in 155 ohms. And then apparently I have to change this one here to my calculated 446 ohms. I don't know why this one goes to the back now. It's a little odd. Okay, so 446 ohms. And then it doesn't allow me to simply measure the equivalent resistance. Oh, by the way, I have to take this one away. So what I do is I put a voltage source in here, a power source, and I put that voltage source as 115 volts, and I'll show you in a moment why I did that. Let me just put one more wire in here, and then let me put an ammeter here in order to determine the total electric current. So let me show you why I put 115 volts on there. Of course, resistance times electric current equals voltage, so that is Ohm's law. And for the total resistance I should come up with 115 ohms. And if I put a battery on there that supplies 115 volts, then I would know that I would have to measure 1 amp, and that's what I'm going to try to do, measure 1 amp. Let's see, there we go. And I'm going to click on this one here, and it says display ammeter. Yeah, that's the one I want. And indeed, I think this is close enough. 0.9989 amps. That's 1 amp. And the negative here is simply, let me get rid of that negative, because I can turn the ammeter around. Notice it says plus on the top, negative on the bottom. I changed polarity. No, that switched. So that really didn't matter. And now it's a positive number. So 0.9989 amps is what I'm measuring of 446 ohms and 155 ohms, which means that I have to have a total resistance of 115 ohms. There's a problem for determining the equivalent resistance in a series parallel combination circuit. In fact, that's all it says for the problem description. Determine the equivalent resistance between the points A and B for the group of resistors in the drawing. Okay, let's see. Let's analyze the circuit here first. The electric current goes in here. Here's a junction. So it goes through here. I need to click on that. It splits up here, and it splits up there, which means whatever comes after that must be in parallel with this one. So all of the stuff here on the right hand side can be considered in parallel with this one. In fact, the current flows through here, flows through here, flows through here, flows through here, comes back to this junction here where it rejoins the other part of the current that it split up from, and then comes back to be the same current. So this resistor is in parallel with everything else. In order to do anything here, well, I first have to look at all these other resistors. Okay, so let's look at the 3.0 ohm resistor. Well, after that, the current splits up, but notice the current goes through here, and then it splits up here, 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 comes all back together, and here it's the same current that it was prior to splitting up. So these two here, this one here, and all the rest here that come after the 3 ohm resistor are actually in series with each other. And again, I cannot do anything with the 3 ohm resistor until I have looked at all of these here. These two resistors are actually the easiest in the bunch. Not only do they look parallel, but they are parallel. The current goes in here, splits up, and then comes back together here, and these two are clearly in parallel. These here, if you think about it, this one here and this one here are totally in series. Sure, they don't look like it in the drawing, but that's just the way the drawing was done. Current goes through here, and then the same current goes through there. So these two are in series. You can draw them here and here, or you can draw one up here and one to the side, or you can draw both of them here on the side. It's all the same. These two are in series. Where to start? Well, either start with these two here in series or start with these two in parallel, but I'll show you in a moment why I start with the two in series. So let me write that down. 4.0 ohms plus 6.0 ohms, trivial. I come up with 10.0 ohms. And now what I'm going to do is I'm going to take this circuit here and copy it, put it there, and I'm going to draw in that, instead of the 4 and 6 ohms in series, I have just one resistor here of 10.0 ohms. That was supposed to be a period. And this one here just goes straight through. There we go. And notice why I started with these two resistors here being in series, giving me 10 ohms, because now I realize that because of this junction here, which is virtually the same as this junction here now, or actually is, the current splits up into three parts. The current that comes in here goes through this one, goes through this one, goes through this one, and those three parts come back together. Here, and here, and here. So these three resistors are actually in parallel. And again, if I look at these two here to begin with, these two are indeed in parallel with this one and this one. What I did now is it saved me some effort realizing that these two here being in series, these two here together, the 10 ohms, are also in series with, in parallel with the 8 and the 9 ohms. So what I'm going to do next is change the color and say that 1 over 9.0 ohms plus 1 over 8.0 ohms plus 1 over 10.0 ohms is 1 over the equivalent resistance on the right hand side there, supposed to be Q. Type it onto my calculator. So I'm going to have 1 over 9 plus 1 over 8 plus 1 over 10. The result of that is 0.336. That small number tells me that I still have to invert it. That kind of decimal number almost always tells me that I still need to invert that. So I do that, and that is 2.98 ohms, maybe around at 3.0 ohms, but I keep my intermediate results in just one more significant figure, and will round later on. So overall, again, I could copy this whole one here, and now I could say that I basically, let's see, I think I'm still in blue, I have a resistor here that is 2.98, at least maybe 2.98 ohms. These two here were in series. That gave me the 10 a while ago, and then I put the 10 into parallel with the 8 and the 9, so which means I totally have an equivalent here for this entire thing here on the right hand side of 2.98 ohms. And that one here is, and notice I got rid of these two junctions here. This one here is now totally in series with the 3.0 ohms, as I mentioned earlier. All of this one here is in series with the 3 ohms, as I tried to explain, with the current going through here. The current goes through here Sure, here it splits up because of these other resistors, but here it comes back together and it's the same current over here as it was here. It's the same current, total current flowing through all of these here together. I guess I could have just left it as 3.0 ohms because I notice it's in series with the 3.0. So on the right hand side here, obviously I have 6 ohms. Again, use a different color here. So I have a total of 6.0 ohms on the right hand side, and that one, as you can see, the current splits up here and then comes back together here, is then of course in parallel. So the total result is therefore 1 over 20.0 ohms plus 1 over 6.0 ohms equals, that is 1 over the total resistance. And that last step, I'll let you do that. Let's see what I want to write here. So therefore R total equals whatever you come up with in ohms. Remember, when you add these here, the reciprocals, you have to still, you come up with a small number, you have to still invert it in order to get the total resistance. A couple of things to say here. Notice that the equivalent resistance in this 3 resistor parallel part of the circuit here is smaller than the smallest one that was given here as the 8 ohms, and the same thing will happen here. The total resistance that you will get here will be smaller than the smallest one you have over here, which means smaller than 6.0 ohms. Keep that in mind. If you don't come up with a number that's smaller, you would have made a mistake. The other thing I wanted to mention is really when you analyze a combination circuit, it does involve several steps. You really have to go through each single part of the circuit at a time. So here the series part, then here the parallel part, then over here the series part, and then finally the parallel part here with the 6 ohms and the 20. For this one here, I actually will show FET, the circuit construction kit. I'll take a moment here, come up. Alright, grab a wire. Actually, I'll grab a resistor to begin with, and then I put another one, let's see, over here, and then there's one over here, and one there, and then there's a couple in the middle here. There we go. Whoops. And now I'll grab the wires. There we go, and there. Of course, my schematic looks in a certain way when I put it together. Overall, it's the same deal, but I want to see how much I can do with a certain amount of wires here, and actually I can do it like this here. I'll put a little wire in there to make it look better. If you look at it carefully, that's exactly the same circuit that you find in the book. Put a battery here. There we go. And oops. There we go. And I put an ammeter right there. There we go. But I still have to adjust the resistances. And let's see, the first one, this one here was 3 ohms. This one was 20 ohms. This one was, I right click on in order to change the resistance. This one was 9, and the next one will be 8. And then this one here was 4, and the one at the bottom is 6. Done. And let's see, I'm going to change the voltage just a little bit. I'm going to try 9.2 volts just for kicks. Yeah, oh, that's nice. 9.2 volts, remember? And I have 2 amps right here. Ohm's law tells me that the total resistance of the entire circuit is divide the total voltage by the total current. So 9.2 volts divided by 2 amps is 4.6 ohms, and that's what you should have come up with when you do go through the calculation that I showed you on paper earlier.